In the previous video, we noted that the pH of a 0.2 molar solution of ammonia would be 11.28. As we add 0.5 mole per liter hydrochloric acid to this solution, we would expect that the pH would decrease. So in part B of this problem, we're asked, what is the pH after you've added 5 milliliters of 0.5 molar HCl? So whenever you're doing a titration problem and you've actually started to add your strong acid or strong base, the very first thing that you want to do is a calculation of the amount of the acidic and basic components that you have. So we're going to be doing this in moles every time. So what's happening as we're adding this acid is this. We have NH3, and then we're going to add our strong acid to it, which is a source of H+, and that's going to produce our ammonium ions. So like I said, you want to be working in moles when you're doing this initial calculation. So initially, how many moles of NH3 do we have? Well, we've got 40 milliliters of the solution, and we get 0.2 moles of NH3 in every liter, or in every 1000 milliliters. So 40 times 0.2 divide 1000, and that is 0.008. So that's how much we've got, 0.008, or 8 by 10 to the minus 3. Okay, so we got that guy. Now, what about the HCl? Well, how much did we add? We added 5 milliliters, and the concentration of the HCl was 0.5 moles per liter, or per 1000 milliliters. So let's see what we get. 5 times 0.5 divided by 1000, and that ends up giving me 0.0025. 0.0025. To begin with, we had none of that. So what's going to happen here is that the H+ is our limiting reactant, so that's going to get all used up, leaving none of that. This will go down by 0.0025 as well, so we can do the math on that. 0.008 minus 0.0025 leaves me with 0.0055. And then this guy over here, our product, is going to go up by 0.0025. 0.0025. So after the addition of the H+, what do we have? We have a mixture of a weak base, and its conjugate acid, aka it's a buffer, right? So we're in the buffer area of the titration curve. We are yet to reach the equivalence point. So when you have a mixture of a weak base and its conjugate acid, you can solve for the pH using the Henderson-Hasselbalch equation. So we're going to go ahead and do that now. So pH equals pKa plus log of moles of base over moles of acid. Now we've got a little bit of a complication because we want to get the pKa, but our acid is an ion. You can see that our acid is an ion, and whenever that is the case, we're going to have to go via the Kb of the base, right? So our pKa is equal to the negative log of our Ka, and we have to recall that Ka is equal to Kw on Kb when we can't get the Ka directly from tables. So this is just going to be negative log of Kw on Kb, where Kb is the base dissociation constant for ammonia. So this ends up being negative log of 1 by 10 to the minus 14 over 1.8 by 10 to the minus 5. So my pKa here ends up being negative log of 1 by 10 to the minus 14 over 1.8 by 10 to the minus 5, and it's 9.26. Okay, Now we already had our moles of base and our moles of acid from our previous calculation at the top here. So there's our moles of acid 0.0025 and there's our moles of base 0.0055. Okay, so pH is equal to pKa 9.26 plus log of moles of base, it's just up there, right? 0.055 over moles of acid, there it is, 0.0025 make sure we get everything copied down correctly, and then that should give us our pH. So let's see what we get. The answer from previous plus log of 0.055 divided by 0.0025, and we end up with 9.60. So let's compare that to where we started. Started at 11.28, and after 5 mils we're down to 9.60. So that problem describes, or this video describes, how we calculate the pH when we're in the buffer region of the titration curve.